Okay, so in this video we're going to find the primitive roots of these sets here. Now, the primitive root is the generator of the congruence classes when they're acted upon by these functions here. And what this means is integers modulo this number in the bottom, so modulo 6, modulo 10, modulo 20, and it's acted on by multiplication. So how are we going to go about finding that? Well, we've got these two tools here which we can use. So Eulers Totient Function, which is phi of n, so that's the numbers which are co-prime up to n. And here we've got Carmichael's number, which acts upon these Eulers Totient Function members of this set. So I'm going to show you how we calculate that. So first of all, let's look at this one. So multiplication acted upon the integers modulo 6. So first of all, we'll work out Eulers Totient Function for modulo 6. So what we're now looking for is all the numbers which are co-prime to 6. So that will give us the set which includes 1, 2 isn't, 3 isn't, 4 isn't because 2 will fit in there, and 5 is the only number left. So phi of 6 gives us a set which contains only the numbers 1 and 5. So phi of 6 equals 2. Now for this set to have a primitive root, Eulers Totient Function must be equal to Carmichael's number. So I'm just going to write that here. Phi of n must equal lambda of n. Now Carmichael's number, which is going to be, let's write that down on, let's do that one here. So we're looking for lambda of 6. So what we need to find Carmichael's number, we need the members of this set here, which we'll call A, to the power of some number k, which is congruent to 1 modulus n. We need the smallest value of k in which we can produce all of these numbers. So in this case it's just the 1 and the 5. So 1 to the power of 1 is congruent with 1 modulus 6. Now whatever we raise this 1 to, we're only going to get 1. So that's the smallest power we've got there, obviously. But now with this number 5, 5 to the power of 1 is congruent to 5 mod 6. So that's produced the first number in the set. Now we need to raise it to 1 more power. So 5 squared, so let's just write that as equals, just to break this down, is 25. And then modulus 6, 25 is congruent to 1 mod 6. So therefore our Carmichael number for this set here is 2, because that's the smallest power in which we can generate both members of this set. So that equals 2. Now we can see here that phi of 6 and lambda of 6 is 2. So therefore a primitive root of this set exists. Okay, so with this set here 1 and 5, this is going to be reasonably straightforward to find out which is going to be our primitive root, because 1 acted upon a multiplication modulus 6 is going to keep generating 1. So if you use the 5, this will be a good way to demonstrate how it works before we move on to the slightly more complicated one for modulo 10. So 5 to the 1 equals 5, which is congruent with 5 mod 6. And now we raise it to another power. It seems very much similar to here, but this is what we need to do here. 5 squared equals 5 times 5 to the 1, which is congruent to 1 mod 6. So if we go again, 5 cubed this equals 5 times 5 squared, which equals 1 times 5, which is congruent with 5 mod 6. So this will keep generating this set here. So we're pretty confident that 5 here is going to be our primitive root for this set. So I'm just going to write down here, primitive root of this one is going to be 5. So that takes care of that. So now let's apply these rules now for our multiplicative function here. So modulus 10 on multiplication. So let's rub this off and let's start with that one. Okay, first of all, let's work out Eulers Totient Function. So let's just write this one here now. Integer multiplication modulus 10. First things first, Eulers Totient Function of 10. So this will give us our set co-prime to 10. We want 1, 2 is not going to work, 3 fits, 4 doesn't because 2 works in here, 5 goes into 10, 6, we've got 2 times 3, 7 will fit, that's co-prime, 8 is not because 2 is a factor, and 9. So now we've got a slightly bigger set here, so we've got 4 numbers. So now we need to calculate Carmichael's number. So now we need to calculate lambda of 10. So again, using the function that we used before, x, so a, let's use a to the power of k is congruent with 1 modulo, this time is 10. Okay, so all these numbers, what's the lowest value of k, which will generate all of the numbers of this set with congruent to 1 mod 10. So 1 we don't need to do, whatever we raise 1 to will always give us 1. So that's fine. Let's start with 3. So 3 to the power of 1 is congruent to 3 mod 10. 3 squared equals 9, which is congruent to 9 mod 10. So we've generated 2 members of the set so far. 3 cubed equals 27, which is congruent to 7 mod 10. So now we've got 3 of the numbers. So now hopefully we can find a 1. So now 3 to the 4 equals 3 to the 3 times 3, which will give us 7 times 3. Let's just get that congruent to 7 times 3, which equals 21, which is congruent to 1 mod 10. So 3 will generate all of the members of the set when k is 4. So 3, just going to put a little line underneath that one now. Let's try 7. So 7 to the power of 1 equals 7, which is congruent to 7 mod 10. It's pretty straightforward. 7 squared equals 49, which is congruent to 9 mod 10. So now we're looking good. 7 cubed, so that is congruent to 7 squared times 7. So that's 7 times 9 is 63, which is congruent to 3 mod 10. And then the last one, number 4, 7 to the power of 4, which is congruent to 7 cubed times 7, which is 7 threes are 21. So that's going to be congruent to 1 mod 10. So 7 will generate the whole set as well. Okay, now we just need to check the last one. So the number 9. So 9 to the power of 1 equals 9 mod 10. 9 squared equals 81, which is congruent to 1 mod 10, and it should be congruent there, mod 10, which is congruent to 1 mod 10, and then 9 cubed, which equals 9 squared times 9, which is congruent to 9 mod 10. So this one is not a generator, so all we're left with here is that 3 and 7 are generators. Now just to check Carmichael's number here, lambda of 10 here is going to be 4, because that's the lowest power at which we can generate all the members of the set. So this one equals 4. And again, this lambda of 10, Carmichael's number, is equal to Eulers Totient number of 10. So we've satisfied this as well. So therefore we can say the generators of this function here, primitive roots, are going to be 3 and 7. Okay, now let's have a look at this set here, modulo 20. Okay, integers acted on multiplication, modulo 20. So let's find Eulers Totient function of 20. So this gives us the set. So 1 is going to be included, 2 won't be, 3 is, 4 won't be, 5 won't be, 6 won't be, 7 will be included, 8 is not, 9 will, 10 won't, 11 will, 12 is not, 13 will be, 14 won't be because it's 2, 15 won't be because it's 5, and 16 won't be, so 17 will and 19 will. So Eulers Totient function for 20 is going to give us a value of 8. Okay, so now we need to find Carmichael's number. So a to the power of k is congruent with 1 mod 20. So let's see what we can generate here. So 1 we know will always keep generating 1, so let's try 3. 3 to the power of 1 equals 3, which is congruent to 3 mod 20. 3 squared equals 9, which is congruent to 9 mod 20. Okay, 3 cubed equals 27, which is congruent to 7 mod 20. So what we're hoping for is we can get up to 8. That's what we're looking for. Okay, 3 to the power of 4 equals 3 cubed times 3, which is congruent to 3 cubed times 3, which is 7 threes are 21, which is congruent to 1 mod 20. Okay, let's try this one now. So if we multiply 1 by 3, we're just going to get 3. So this is going to give us 4. So 3 is not going to be a generator. Let's try 7. 7 to the power of 1 equals 7, which is congruent to 7 mod 20. 7 squared equals 49, which is congruent to 9 mod 20. 7 cubed is congruent to 7 squared times 7. So 7 squared is congruent with 9 mod 20 times 7 is 63, so that's going to give us congruent to 3 mod 20. 7 to the 4 is congruent to 7 cubed times 7. So 7 threes are 21. That's going to give us a 1 mod 20. So that's multiply that 1 by 3. That 1 by 7. We're back to the 7 again. So 7 is not a generator. So 1, 3, and 7 not generators. Okay, let's try 9. 9 to the power of 1 equals 9, which is congruent to 9 mod 20. Okay, 9 squared equals 81, which is congruent to 1 mod 20. So again, multiplying that by 9, we're going to be back here. So 9 is not a generator. While 11, we've got 11 to the power of 1 equals 11 mod 20. And 11 squared is 121, which is congruent to 1 mod 20. So again, multiplying that by 11, we're going to be back at this one here. So 11 is not a generator. So 13 to the power of 1 equals 13, which is congruent to 13 modulo 20. 13 squared equals 169, which is congruent to 9 mod 20. So let's go to 13 cubed. So instead of calculating 13 cubed, we can say it's congruent to 13 squared times 13. So 9 times 13 is 117 mod 20, which is just going to leave us with the 17. So I can take this number out here. 13 to the 4. So again, I won't calculate it out. I'll go 13 cubed times 13, which is congruent to 17 times 13. So 17 times 13 is 221. 221 will lead us to a 1. So that's congruent with 1 mod 20. So again, if we multiply by 13, we just end up back here. So 13 is not a generator. Let's try 17. Let's put a line here. 17 to the 1 equals 17. Let's go into 17 mod 20. 17 squared. 17 squared is 289. Just a quick calculation on that one. We know that that is going to be congruent to 9 mod 20. 9 times 17 will be the next. So 17 cubed, which is equal to 17 squared times 17, which is congruent to 9 times 17. 9 times 17 is 153, which gives us 13 mod 20. 17 to the 4 equals 17 cubed times 17, which is congruent to 13 times 17. Well, 13 times 17 is 221. 221 is back to our 1 mod 20. So 17 is not a primitive root. And then the last but not least, we'll try 19. So let's just, let's do it here. 19 to the 1 equals 19, which is congruent to 19 mod 20. 19 squared equals 361, which is congruent to 1 mod 20. And again, as what we know is when we get to the 1, multiply that by 19, we just end up back here. So the largest number we can get here using the formula a to the k is congruent to 1 mod m. Make that big bigger. Mod m. In this case, its number, our value of k is 4. So our Carmichael number of 20 equals 4, which does not equal 8, which is our Eulers Totient Function of 20. So therefore, using this formula here, we can see that this here definitely does not have a primitive root. So for number 20, this one here is the empty set. Okay.